Today, it's my pleasure to introduce our speaker, Hilka Contro. Hilka is a PhD candidate with Martin McInnes. Hilka's from Finland originally, although you'll notice a small Irish accent too as well, which might be confusing at first glance, but it'll all come together soon. Anyway, so Hilka completed her undergraduate degree in organic chemistry at the University of Helsinki, and she completed her master's degree in clinical biochemistry and a second master's degree in exercise physiology at the University of Jyväskylä. I didn't say that correctly, but anyway, it's also in Finland. I think it's in Western Finland, right?
Central Finland.
Central Finland. There we go. Anyway, so in 2019, she came to the University of Calgary to start her PhD in exercise physiology with Martin, and she's been here since. The Irish part all comes together, where she was a research assistant at the University of Limerick in Ireland. Her partner is also Irish. There's some, happenings there where now she has this great accent, which is confusing. Okay. Aside from all of that, if you don't know anything else about Hilka, she wrote here that she's an avid cyclist and runner, but that's really downplaying the avidness of her cycling and running. She is an incredibly fit and fast cyclist and runner. And if you really want to feel out of shape, I suggest you go running or cycling with her. It's great fun. Yeah. So I don't know. How many you spend like many hours a week on Zwift still, don't you?
Now in the summer?
Yeah, not in the summer, of course, again. In the winter. Yes. Yes. So, training less. Yes, yes. Okay, so Hilka's planning to defend her PhD at this says the end of 2023, beginning of 2024, so in the very near future. So today she's going to give us a nice little kind of overview of some of the work that she's been doing, and her work is titled Sex Differences in Hematological Variables in Male and Females Matched for Aerobic Fitness. Over to her.
Thanks, Michael. Okay, so when I picked this title, I wasn't really sure what I'm going to present, so it's not so representative of what I'm actually going to talk about. It's a part of it, but it's only the second half of it. So I'm going to also talk about some studies that kind of give background to what we're looking at here, because I know there's a lot of biomechanists in the room, and maybe you're not so familiar with the aerobic fitness side of it and the physiology that matters for aerobic fitness. So first, I'm just going to introduce hemoglobin mass and why it matters for aerobic fitness. Why do we care? Then I'm going to introduce a study. The first one I did here, carbon monoxide inhalation and what it does to performance. And then another study that's kind of related, which is phlebotomy and performance. And then I'm going to quickly talk about some studies we did in collaboration with the University of Guelph, where we looked at adaptations after blood flow restriction training. And then I'm going to get into the hemoglobin mass and associated variables, so vascular volumes in fitness-matched males and females. And then I'm going to talk a little bit about estimating hemoglobin mass and blood volume from other variables. Okay, so anyone who follows running, maybe you noticed last Sunday, the women's world marathon record was broken. The Ethiopian Tigst Assefa, she ran a 2:11 time, took 2 minutes off the previous record. And this is about 3.5 minutes faster than Paula Radcliffe's record that still stood a few years ago and was considered almost unbreakable. So it got me thinking about what kind of physiology she has to have. There's a lot of speculation now. Is this time legit? Is it the shoes? Because she's wearing these shoes that are $500 and they're disposable, so you wear them once and then you throw them away, and maybe they're like make your running economy so much better. That's why she's running these times. But I think there must be physiology there as well to explain this. Maybe you as biomechanists disagree. Maybe it's all the shoes, but we can look at that. Just some determinants first of VO2 max and endurance performance. So maybe you've heard VO2 max, even if you don't really use it if you're looking at tendons or whatever, but it is the maximal rate of oxygen consumption that we achieve in endurance exercise. But it's not the only thing that matters for endurance performance. So we only sustain VO2 max for a few minutes. But what matters more in endurance running, like marathon, is what percentage of the VO2 max you can sustain over the whole race. So that's the performance VO2. And then also your running economy, or in cycling efficiency, that determines how much speed or power we get for given VO2. So that's not a constant either. So if you're more efficient, you can go faster for the same VO2. And those three together, the VO2 max, the percentage of VO2 max, and running economy, they determine distance running performance. So what goes into VO2 max? Well, we notice a few steps in the oxygen transport cascade that could be limiting. There's the pulmonary diffusion capacity, so how well are we oxygenating the blood in the lungs? Then there's the transport, basically cardiac output and the oxygen carrying capacity, so how much hemoglobin you have in the blood, how well you're able to transport it, and then there's the muscle that's gonna take up the oxygen and use it. And in theory, any of these steps could be limiting. But we know that especially in trained athletes, it tends to be the cardiovascular system that's the bottleneck. Typically, the skeletal muscle capacity is overbuilt, so there's more mitochondria there that are actually needed for VO2 max, at least in whole body exercise. There could be a limitation in the lung if, especially in some well-trained athletes, you can see arterial desaturation. But in general, it's the cardiovascular system that becomes limiting. So the way we can describe VO2 is the Fick equation. It's very simple. It's cardiac output. That's the Q here. And then there's the oxygen extraction. So this is the arteriovenous oxygen difference. So how much oxygen we have in the artery when we're sending it to the muscle, and how much we have in the venous blood that's returning from the muscle, right? I also have a little limerick for you by ChatGPT that explains it in a more fun way. I thought it was pretty good, so I put it there. So we have cardiac output, so it's liters per minute blood pumped by the heart through the whole body, or also flowing through a limb if we're looking at a single limb. And the AVO2 difference represents extraction, how much we're sending and how much we're taking out of it. Okay, so if we look at blood and what it's composed of. In a typical human, we have about 4 to 8 liters of blood. It depends on body size and sex and fitness. We're going to look into the variables that determine it. But if we spin the blood down in a centrifuge, we get 2 layers. We get the plasma on top, and we get the red blood cells at the bottom. And then there's less than 1% other things, white blood cells. But the percentage of red blood cells in the whole blood is the hematocrit. And so hemoglobin mass, that is the overall amount of hemoglobin protein in that whole blood volume, right? So it's not the concentration. The concentration can be anywhere between 12 and 17 grams per deciliter. But then if we look at the concentration and the volume, we get hemoglobin mass. This is another schematic. Blood volume is plasma, and red blood cells, and hemoglobin mass resides in the red blood cells. Okay, so how can we measure hemoglobin mass? When I came here in 2019, I helped to set up the method here in the lab, and then I've been working with the method since in all my studies, basically. It's pretty simple. What we're doing is we're giving the participant a small amount of carbon monoxide. And what that does is it binds to hemoglobin. It has very high affinity to hemoglobin. So it's going to replace oxygen from the hemoglobin molecule and sit there tightly. So it's going to label the molecule, basically. So this is just a figure showing the initial situation, there's very little carbon monoxide at baseline. There's always a little bit. There's the blue molecule here. And then we give a known amount. We know exactly how many milliliters of carbon monoxide we give to the person. And we take a blood sample after the blood has properly mixed. And then we see the fraction of labeled hemoglobin, and we can calculate back how much total hemoglobin they must have to achieve that fraction, right? So it's the dilution principle. If we see a large change in the carboxyhemoglobin, it means that the person has a smaller hemoglobin mass. But if we see only a small change, they must have a larger hemoglobin mass because it's diluted in a bigger amount of protein. So it's a pretty simple method, works pretty well, good reliability. And then when we have hemoglobin mass, we can also calculate the vascular volumes. So plasma volume and red blood cell volume from that. So this is our bucket of blood. We have this many liters of red blood cells, this many liters of plasma volume. There's the equations to do it. It's pretty straightforward. We just use a little correction factor here for hematocrit, because when we measure it from the venous blood, it might not represent whole body hematocrit because the hematocrit changes in different vessels. So this has been accepted as the correction factor. So why is hemoglobin mass associated with aerobic performance? Well, it's basically a good surrogate for the overall capacity to transport oxygen. If we look at the thick equation here, VO2 max, we would be at maximal cardiac output here. And then we have the arteriovenous oxygen difference here. Well, hemoglobin mass affects both the arterial oxygen content here and the stroke volume here, because it's tightly connected with blood volume, which affects stroke volume. It might be a little bit hard to get your head around why the hemoglobin mass and not the concentration matters, but I'm going to try and explain this. So hemoglobin mass is basically a very stable marker. If we get dehydrated, we're going to have an increase in the concentration of hemoglobin, so the arterial content goes up, but the stroke volume goes down. So the delivery kind of stays similar. Or if we're getting a plasma volume expansion, then we have a lower hemoglobin concentration, but then we have an increase in stroke volume because we have a better venous return. And our delivery will stay roughly the same again. This is just a figure to illustrate what it is. We have more blood. That means we have better venous return. That's going to fill the heart better. And we get a higher cardiac output. Okay, so if this is the case, do athletes have more hemoglobin mass than untrained people? Yeah, that's pretty well established. Here's one figure showing athletes of different disciplines. We have untrained, these are all males. Untrained males, about 11 grams per kilo body mass. Then we have downhill skiing, so they're a little bit fitter, but it's not really an aerobic sport. We have leisure sportsmen, so maybe recreational runners. Swimming, triathlon, junior cyclists, runners, professional cyclists. You can see the higher the aerobic demands of the sport, the higher the hemoglobin mass. Okay, so does exercise increase the concentration of hemoglobin or hematocrit? I think a lot of people have this misconception because we know, for example, in professional cycling, they used to have hematocrit limits that the athletes couldn't breach, and also cross-country skiing, they have hemoglobin limits. But in fact, training tends to have the opposite effect, if anything. We know that the more trained group we're looking at, the lower the hematocrits tend to be. So why is it that we could see very high hematocrits in athletes? It could be altitude training. That's a legit way of increasing the concentration of hemoglobin or your hematocrit. But it could be doping. If you use EPO, erythropoietin, that's going to stimulate the production of red blood cells. or it could be blood transfusions. There could be genetic disorders as well. For example, this Finnish cross-country skier, Eero Mäntyranta, he had a condition that caused a mutation in the EPO receptor, and his erythropoiesis was constantly on, basically, and he had very high levels of hemoglobin. And he won a few gold medals as well. So we know that athletes don't have a higher hematocrit, but they do have an increased hemoglobin mass and a blood volume, up to 40% more than untrained individuals. And we can see it if we look at the relationship between hemoglobin mass and VO2 max. Here's VO2 max in milliliters per minute and total hemoglobin mass in grams. So these are absolute values, and the correlation is very good. However, the confounding factor here is body size. Of course, if you're big, you're going to have a higher absolute VO2 max, but you're going to have more of everything, all the proteins. So if we normalize to body mass, we get VO2 max in a relative value, normalized to body mass and hemoglobin mass as well, grams per kilo. And we still have a relationship. It's not quite as good, but it's still pretty strong. But here, if we look at the concentration of hemoglobin, there's no significant correlation here with VO2 max. Something we also know now is that the limitation we have to VO2 max might be dependent on your fitness level. This is a meta-analysis by Øyvind Skattebu from Norway, where he looked at all the studies that had been done where they had directly measured oxygen extraction and cardiac output in both untrained and trained people. And here you can see the gray line here is set to 1. So these are just fold differences. So untrained are set to 1, and then the athletes are compared to those values. So we can see that there's a small decrease in the arterial oxygen content in athletes, as we could expect, because they have lower hematocrits, right? So their oxygen carrying capacity is actually a little bit impaired. However, the AVO2 difference is greater. So maybe they're sending a bit less, but they're actually getting more out of it, out of the blood. So you can see it in the extraction value. They can extract 90% of the oxygen at VO2 max, whereas untrained people are extracting 71. But the biggest difference here is in the cardiac output. And that's going to be the one that really explains the big difference in VO2 max. So you can see the athletes here have about 80% higher VO2 max than untrained people. And most of it is explained by the cardiac output and not the extraction. The extraction also matters, but when you're at 90, you can't go much higher, a little bit higher maybe, but the delivery side is the one that's going to make a difference. So, okay, leading into the first study I'm going to present here, the effects of carbon monoxide inhalation on maximal and submaximal performance. What we did in this study is we want to see how changing the arterial oxygen content by giving a little bit of carbon monoxide to people would affect their VO2 max and also their MLSS threshold, which is the maximal lactate steady state threshold. And we hypothesized that VO2 max and MLSS would both be impacted by this, and that the reductions in aerobic fitness would be dependent on fitness. So fitter people would suffer more. So we had 20 people come into the lab and do a ramp test. And before the ramp test, they would inhale either carbon monoxide or they would do a sham condition. You can't tell whether you get the carbon monoxide or not because it's flavorless, colorless gas. And the amount we gave was small enough not to induce any side effects. And we actually confirmed this. The blinding was successful. So people guessed after which one they were getting, and it was kind of 50-50. They couldn't get it right. Then we also found their MLSS, so the highest constant load intensity where lactate is still stable. So once you're above this threshold, there's no steady state in lactate, it keeps going up and it feels way harder and you're gonna stop eventually. So we found the intensity, and then we did the same. They inhaled either carbon monoxide or did the sham and rode 30 minutes at MLSS. We took blood samples and then analyzed what happened. First, this is just to show that the intervention was effective. So we managed to increase their carboxyhemoglobin to about 6% from about 1% in both these experiments. And the effect that has on the effective hemoglobin concentration is about 5%. So they would have just about 5% less available hemoglobin than they would normally have. And that change would be then reflected in the calculated arterial oxygen content. So not a huge drop, but still it might make a difference when you go hard. And that's exactly what we saw. We saw a reduction in the thresholds, not a significant one in the first. This is the first ventilatory threshold. But in the second one, the respiratory compensation point, we saw a significant drop, and also in the VO2 max. And also when we then plotted the decrease in peak power output in these RAM tests against the fitness level of the people, we saw that indeed the fitter people had a bigger decrease in peak power output. Some of the untrained ones didn't really change. Also, if we look at the VO2 max values, we had the same pattern here. The triangles are males and the squares are females here. So both in males and females, we saw the same pattern. So fitter athletes suffered more. Also, we look at the MLSS to see whether the lactate was destabilized after this carbon monoxide. And what we saw, it was actually destabilized. So we could say that they were not at their MLSS anymore. The lactate was drifting up. So the black line here, or the black circles, this is the sham condition, and the white circles are the CO condition. But then we looked at the data a bit closer, and not everyone had the same response. Some people were actually stable, and others went straight up, and some couldn't even finish the 30 minutes. So when we looked at the ones that were stable, this is the upper figure here. And then the ones that were not stable, we had two different groups. And analyzing their different characteristics, we noticed that the VO2 that these unstable people were riding at was higher than in the stable group. So they were the fitter people that couldn't stabilize their lactate after the carbon monoxide. Same with VO2 max. So clearly, again, the ones who are more aerobically trained, they suffered more from the carbon monoxide, and the lactate wasn't stable anymore. Okay, so that's one intervention we could do, give a bit of carbon monoxide to people. Another one would be just to take out blood. So my second study, I looked at what happens if we do a blood donation before exercise. Both to VO2 max and some indicators of exercise-induced stress in submaximal exercise. We hypothesized that the phlebotomy would reduce VO2 max and also affect submaximal responses, and also that the reductions in fitness would be dependent on fitness. Same thing. So we had 17 people in this study, and they went through a few pre-trials. We measured their ramp performance. We also did a familiarization to this. We basically repeated the control ride twice, also for reliability measurements. And we measured their blood volume so that we could take a standardized amount, 7% out of the blood volume away. We had a sham condition here, so not everyone got actually phlebotomized, but half of them got sham phlebotomized. We put in a catheter, there was a curtain, so they couldn't see whether the blood was actually taken out or not, just to make sure there's no psychological effects here, because people know that blood donation might affect your performance after. So just to reduce that. And the controlled ride was a 60-minute ride at a pretty hard intensity in the heavy domain. So it's going to be between the thresholds. It was about 70% of VO2 max. And after that, they did a maximal time to exhaustion test. In the experimental ride, we did the exact same, but they just did this phlebotomy first, or the sham if they were in a sham group. Same thing. What we saw is the VO2 max was probably reduced. We actually didn't get a significant change here in VO2 max, but in the time to exhaustion, there was a reduction after the phlebotomy. Also, if I plot the reduction in VO2 max against fitness, we kind of get the same pattern, where it's not really powered here to see a very good correlation here. But I think if we had double the amount of participants, we probably would have a similar phenomenon happening here. So the fitter people got worse, more worse than the less fit. Okay, they will look at submaximal responses in the heavy domain, because this is something that's kind of lacking in the literature. We know that the peak performance might be impaired, but what happens when you're riding at just 70% of your VO2 max? And we saw that phlebotomy increased ventilation, so they were breathing harder. These are our relative changes compared with the control ride. So the people who got phlebotomized, they are the squares here. They were breathing harder. They also had an elevated lactate and an elevated heart rate compared with the control ride. People in the sham group, they were actually all a little bit better in these. Maybe there was a training effect after doing a set of repeated testing. So they were actually a little bit better. Okay, so if we go to the literature, this kind of confirms these two studies, what has been observed before. For example, in this figure, this is from Schmidt and Prommer, who are experts in hemoglobin mass. They just plot a few different interventions in this graph, whether a change in VO2 max is associated with a change in hemoglobin mass, or maybe the other way around, makes more sense. So phlebotomized people, they lose VO2 max in general. And if we increase hemoglobin mass by EPO, we can see an increase in hemoglobin mass, VO2 max also goes up. So it seems like there's a causal relationship between these variables. Also, if we look at training interventions, this study was 9 months of endurance training. And we can see how VO2 max improved, or this is the change in VO2 max. It was correlated with the change in hemoglobin mass. So it seems like the people who increased their hemoglobin mass the most also increased their VO2 max the most. More evidence for causal relationship. So these studies like to show they do confirm what's been found before, but they also expand on this by demonstrating that it also affects submaximal intensities and your thresholds, not only your peak power and your VO2 max. Okay, so this is a side project that I was roped into that turned out to be really interesting, because I had set up the method here for hemoglobin mass. A student of Dr. Jamie Burr in Guelph reached out to me. He wanted to do some research with this method because he's been looking at blood flow restriction training. And it's a form of training where you basically have these cuffs or something that stops blood flow to your legs or reduces it. And it's more known maybe in strength training, rehab, and we know it's gonna maybe increase the hypertrophic response, so you have to do less mechanical load for the same hypertrophy. But also, several studies now have found that if you do aerobic training, just light, very low intensity training with these cuffs, you can see big improvements in VO2 max, which is kind of surprising. And no one has really established why. Maybe because of the history, the tradition, it comes from strength training. People were looking at the muscle. They were looking at mitochondrial volume, capillarization. Is it something there that's explaining this VO2 max? But hasn't really been anything that really explains it. Also, some studies show big improvements in pretty highly trained athletes that are already pretty fit. And we know that usually it's a central limitation, as I already talked about. So it would be surprising if just the increase in mitochondrial volume explained that increase in VO2 max in these trained athletes. So Kyle here, he thought it must be blood volume. No one had thought about that. But he presented some pretty cool data that they had collected in the laboratory from acute responses. So you do 20 minutes of this treadmill walking with the cuffs on, and then he measured some blood pressure regulating hormones. Some of the hormones went through the roof, like insane. It's almost similar response that you would get if you lose a lot of blood. And that's because the cuffs block the venous return, and a lot of the blood gets pooled into the legs. And that's a major cardiovascular stressor. So it's not just a metabolic stressor in the muscle, it's also a cardiovascular stressor. And he thought maybe there's going to be a compensatory mechanism then happening that's going to make you increase your blood volume over time. And I thought that's a really good hypothesis because, of course, when you're looking at hemoglobin mass in your research, you think that's going to explain VO2 max, and like that's the only thing. First, we saw that the training was effective. So he had two groups, actually three groups. He had a control group that only walked on the treadmill with no cuffs on. Then he had a group that was high frequency group. They trained 2 times a week on the treadmill. And I can tell you, this is not fun. Like it's very hard. It was people in the lab that's during COVID. So all his lab members were doing the study. So twice a day, they hopped on the treadmill and walked with the cuffs. But then there was also a low frequency group after they opened up the lab. They had some people do it 2 times a week, just a little bit longer, 6 weeks instead of 4 weeks. And they did see what's been established before, that VO2 max went up in the groups that trained and not in a control group. So it was doing something. But then when we looked at the hemoglobin mass, there was no change in hemoglobin mass or blood volume or plasma volume. Nothing changed there, which was a disappointment. Pretty surprising to us. But of course, Kyle was then getting even more anxious about this problem. Like, it wasn't blood volume, it's not the muscle, what is it? So he kept talking with Dr. Jose Calvet in Las Palmas. He's an expert in basically cardiac output, like blood flow. He does direct measurements of oxygen extraction in the muscle. And somehow he convinced his supervisor to start this collaboration with Calvet. It's really hard to do these measurements in Canada, what you wanted to do, because they're very invasive. You have to put in arterial catheters, and it's very hard to get permissions for that. So instead, they decided to fly over to Las Palmas to do these measurements. And it became a pretty big project. A lot of international researchers joined in. And I was lucky enough to be also invited to do the hemoglobin mass measurements. So this happened this spring. We went there in February for the first time, February, March, for some pre-testing. And then we went again for some post-testing a few weeks later. So the purpose of this study was to finally figure out why BFR training increases VO2 max. And Kyle wanted to recruit really well-trained athletes for this. So the minimum requirement for VO2 max was 60 to be accepted in the study. He didn't quite reach that. Some people were a bit lower, but then he also had some athletes with a VO2 max of 80 to balance it out. So it was a pretty fit group overall. Half of the researchers were also participants. So a lot of his PhD students were also doing this study as a participant, and myself as well. I was a researcher, but I also did a study as a participant. So that kind of reduced maybe the cost a little bit. So they were the same people that were tested and testing. So we measured everything. We measured, of course, VO2 max and time trial performance. We did direct measurements of oxygen extraction and leg blood flow. They had a really good echo ultrasound. So we measured cardiac dimensions and function before and after. I did the hemoglobin mass and vascular volumes. We measured the with hyper reflex before and after. And also we took a biopsy to make sure we're not claiming something, even though this has been done before, but maybe we're missing something. So we took biopsies for mitochondrial parameters and function and capillarization as well. These data are still being analyzed. It was a very big study. You can see the whole research group here, how many people were involved. So Kyler really wants to know the answer to this question, that he actually organized this whole thing. And I had the data for the hemoglobin mass, and I can spoil the surprise here. There was no difference. So it's not that. We made sure this time to be, we made sure to be really careful with standardizing everything, because some things like plasma volume is so sensitive to small differences in what you did the day before, for example. So we standardized everything and we're super careful. We did it twice in a row instead of once to make sure we're getting the same values. We can be super confident in the data we're getting and still no difference. So it's not hemoglobin mass that explains it. The other things I'm not sure about. So everyone is responsible for their own little piece of the project, but we're going to find out eventually. Okay, so then to the final study I'm presenting here, sex differences in hemoglobin mass and blood volume. So I've been talking about the general relationship between hemoglobin mass and fitness, but do males and females differ in this context? We generally know that males have a higher hemoglobin concentration. So what about the other variables? One thing here is we have to match for fitness. There's a lot of papers out there reporting values for males and females, but now, as has been established, fitness is another factor affecting these values. So if we know, make sure that we're looking at the same fitness levels in the comparisons, then how do we know it's sex difference and not a fitness difference? This is one example to illustrate what it might look like. This was from a study where I recruited specifically endurance trained people and untrained people. And you can see their hemoglobin mass depends on their training status, both in males and females. Same with blood volume. So if you were to not care about fitness, you might recruit untrained males and trained females, and you might conclude that there's no difference in hemoglobin mass. Or maybe you recruited trained males and less trained females, and you see a difference in blood volume. But then it wasn't actually a sex difference. It was a fitness difference as well. So that's why I looked at all the data I've been collecting so far, because I have a few studies now where we measured the same things. So we measured body composition to get fat-free mass. We did a ramp incremental test to get VO2 max and thresholds. And we measured hemoglobin mass and vascular volumes as well. So pooling all these data together gives a pretty nice data set. And the fun thing about this data set is that it's fitness matched. And what I mean by that, I'm going to explain now. So males obviously were bigger. So they're taller and they're heavier and they have a lower body fat. And because they're bigger, they're going to have a higher absolute VO2 max as well. So these are the VO2 max values. Females, red, and males are blue. And then when we normalize to body mass, the difference is reduced, but it's still there. But if we normalize to fat-free mass, the difference disappears. And we think that this is the most valid way of doing this, because it's not your adipose tissue that contributes to VO2 in any way. It's sitting there, but it's the skeletal muscle mass and it's the lean body structures that can contribute to the oxygen transport and utilization, right? It's not a perfect proxy for it, but it's better than whole body mass. So it's a better indicator of the actual physiological fitness level. Okay, so we had these fitness matched groups. Then what do the hemoglobin mass values look like if we look at the different normalizations? These are absolute values. As expected, males have more. Normalizing to body mass, reduce the difference a little bit, but it's still a pretty big difference. But then normalized to fat-free mass, we would expect maybe to become smaller, but it's still very significant. So even normalizing to fat-free mass, we can say that males have more. If we look at the red blood cell volumes, we see the same pattern, which makes sense because that's where the hemoglobin sits, in the red blood cells. How about blood volume then? In absolute terms, males have more, but when we normalize to body mass, it's reduced. And actually, when we normalize to fat-free mass, it flipped a little bit in the favor of females in this data set. And that's because females had more plasma volume. So again, normalized to body mass, remove the difference, and then it flipped in favor of females when we looked at plasma volume per kilo fat-free mass. I also looked at the relationship between hemoglobin mass and fitness now in both males and females. So you can see the regression looks pretty similar. The slope is pretty much the same. If we look at relative hemoglobin mass and relative VO2 max. And also if we normalize both to fat-free mass instead. But what you can see here is females are a little bit higher. So the line lies a little bit higher than for the males. So for a given hemoglobin mass, say 10 grams per kilo, males would be just under 40, females would be just over 40 for VO2 max. So clearly females have a little bit more VO2 max for the same hemoglobin mass. So just to conclude, I have the absolute values here as the bucket. So the bucket is smaller for females. They have less of everything. Males have more. Then normalized, this arrow is the relative difference between males and females. So females, again, have less, even if you normalize it. And males have more. But in plasma volume, females have more if we normalize it to fat-free mass. Males have less. But they were fitness matched. So how come they have the same fat-free mass normalized VO2 max, even though females have less capacity to transport oxygen? Because that's where the oxygen is bound to the hemoglobin and not the plasma. So it seems like a similar aerobic capacity may be achieved by different oxygen delivery and extraction strategies in each sex. Going back to the Fick equation here. So we remember this is the cardiac output. This is the extraction part of it. Arterial minus venous oxygen content. And we know males have a higher concentration of hemoglobin, so they have a higher concentration of arterial oxygen. I'm not so sure about the stroke volume thing. I've been looking into it, but I'm not an expert in cardiac adaptations. But it seems like in fitness matched individuals, stroke volume might be similar in both sexes if you normalize to body mass. So, for example, in this study, they had highly trained males and females. In absolute terms, stroke volume was greater in males, but when they normalized to body mass, it was similar. So maybe the Q part here is similar in both sexes, but still males have had more because they have a higher arterial oxygen content. So therefore, we think that central oxygen delivery is probably higher in males than females. So to achieve the same VO2 max, females must be extracting more oxygen. That's the only conclusion. Otherwise, the numbers don't match up. And that's exactly what was found in this study. Females were extracting 19% more oxygen than males. Okay, a few words about the methodology in these studies. We're not sure if it's okay to normalize blood volume and plasma volume to fat-free mass. because adipose tissue is also vascular, even though it's less so than skeletal muscle. It also has to be perfused. And we know that at rest, for example, about 5% of blood volume is directed towards adipose tissue. So maybe that's why females have more plasma volume. They have more adipose tissue, and they need to have that overall volume higher so that they can perfuse all the tissue. There's another factor. The way we measure vascular volumes here is we calculate them from hemoglobin mass using hematocrit. And we're doing one assumption here. We have to assume that the venous to whole body hematocrit is the same in males and females. But there's some data suggesting that it might be different in females. But it's hard to know because the papers that have directly measured both plasma volume and red blood cell volume by labeling both compartments with a radioactive isotope, there's very few of those studies, and they usually have been done in clinical populations, and they're not healthy, active, fit people. So there's a question mark, just something to keep in mind. It would change our conclusion a little bit. We would be overestimating plasma volume in females if that were the case. So we're not sure. Okay, so final thing. Now that I have all these data of a lot of people with hemoglobin mass and blood volume, can we estimate those parameters from other parameters? We know that there's good correlations. So I just did a multiple regression. I put in all different variables to try out which ones would improve the model, and I can get a pretty good predicted hemoglobin mass versus actual hemoglobin mass. Same for blood volume. So the R squared would be 93% here, and a little bit less for the blood volume, 88%. The variables that were improving the model I found was fat-free mass and VO2 max. These two were the best ones, the most important ones, explain most of the variation. But then also the concentration of hemoglobin and height, they improved the model. So now I have a little calculator where I can put in these values if I haven't measured hemoglobin mass and blood volume, and I can still get a pretty good estimate, I think. That's the model. So going back to the beginning, where we talked about the determinants of running performance, I'm curious what kind of VO2 max the new marathon world record holder might have. So you can kind of go back to think about what is the minimum VO2 max she has to have to achieve that time. And what is the estimated hemoglobin mass and blood volume required to achieve that VO2 max as well. So there's a few assumptions I have to make here and estimate some parameters. But we know that her marathon pace was about 3 minutes and 8 seconds per kilometer. And if we assume exceptional fractional utilization of VO2 max at marathon pace, so she was holding 85% of her VO2 max over those 2 and a bit hours, and she has excellent running economy, then she still has to have about 70 mils per kilo body mass per minute VO2 max to be able to do that. And that's not an exceptional value for a female athlete. There's been reports before. Paula Radcliffe was around the same, so it's possible to achieve. And if I now plug in these values in my calculator, just assuming normal physiology otherwise, she would have about 13.6 grams per kilo hemoglobin mass and 108 milliliters per kilo blood volume. If we put that into context, these are data from Schmidt and Prommer, who have probably the biggest database of standard values in populations that are differently trained, untrained, leisure sportsmen, regional level, national elite, international elite, highest values ever measured. She would be around here, like higher than normal international elites, but not the highest values ever measured. So I think it's physiologically possible for, I mean, yeah, we know that 70 is an achievable VO2 max, and these are the kind of values that are needed to achieve it. So maybe it comes down to the shoes then. that was all. Thanks for listening.
So who would like to start us off? Question. Steph.
So I'm wondering if so you defined like fitness level in your sex differences study as VO2 max. Is there like, and you have your trained males and females, like is trained male the same as a trained female? Like I always wonder if that is an additional kind of thing, like where like very elite males are trained different volumes and different.
Yeah, that's a good point. I avoid saying they're matched for training status because we don't really know their training status. We know their fitness level, and we just define the fitness level as VO2 max per kilo fat-free mass. But it could be that males and females need different training volumes to achieve the same VO2 max. So they could be differently trained to achieve the same. So that's a good point. Like it could be, for example, that females need to train a little bit more to achieve the same level of fitness, but I don't know that that's the case. Yeah, it could be.
And then how do you think, say if you met, if you consider instead define fitness level as like training volume or something, so you had like runners and load and whatever. How do you think that would affect the sex difference results that you have? Like,
yeah, so as I said, if they both sexes needed different levels of training to achieve the same VO2 max, that would probably underestimate basically effective fitness in one of the sexes. So say maybe that the females had to train twice as much to achieve the same VO2 max. Maybe that was the effect of the training that they've been doing, those adaptations, the plasma volume, for example, and not a fitness difference per se, not like an intrinsic fitness difference. So yeah.
I'm just wondering with your carbon monoxide inhalation procedure, can that be used as a training methodology?
Yes, it actually has been. There's been a couple of papers. Yeah. You need to do it very regularly to get an increase in hemoglobin mass, but it's kind of an alternative to altitude training. If you do that on a daily basis, you're going to have a chronically elevated carboxyhemoglobin. That's going to affect your erythropoiesis, and you're going to produce more hemoglobin. Yeah.
I don't know anything about this, but just as a layperson, if somebody recruits me for a carbon monoxide study, I just say no. Do I have a misconception? I always thought carbon monoxide was a bad thing.
It's not just a bad thing. We produce it endogenously all the time. It's actually a breakdown product of hemoglobin. So everyone walks around with about 1% of carboxyhemoglobin anyway. And if you happen to be in heavy traffic and breathing a lot of exhaust, you might have higher levels. Smokers walk around with 5 to 7 to even 9% if they're heavy smokers. It's only bad if you get too much of it. So in these studies where they have been giving people a carbon monoxide dose every day, of course, it's highly regulated how much they give them, and you can't really overdo the dose. For example, when I do the hemoglobin mass measurement and I give them carbon monoxide, it's a syringe that's only so big. Even if you accidentally fill it too much, it's not going to be a dose that's, harmful in any way.
Questions?
So in the one where you took the blood samples, so you said that you did a 7% of took 7% of the blood, blood volume. How does that relate to like percents that they take in normal blood donation?
It averages out to pretty much like 1 unit, so about 450 mils. That's kind of the standard blood donation unit if you go and donate blood. We wanted to keep it kind of similar to that, but then also make sure that we're not taking more from a small person relative to a big person.
Okay, so like when you get a blood, you go and donate blood, they don't do it relative to.
No, they don't. It's just a standard unit. Okay. So that's why small females might actually feel more effects than a big male. Yeah.
Another question. So this better extraction in females, is there like the better oxygen extraction, AV extraction rate?
there a rationale for why that occurs? Or is it just?
That's a good question. I don't know the answer. I've been doing some reading. It might be there's some evidence showing that females are able to maintain a higher capillary hematocrit than males. And that's gonna drive the extraction. Basically, it's gonna maintain a higher PO2 difference between the capillary and the muscle fiber, help extraction. Females also have more type 1 fibers generally that are usually they have better capillary supply and they are very oxidative. So that might also enhance the extraction. Yeah, I don't know for sure what the reason is.
Okay. That's cool. Yeah, it seems like it'd be easier to say, oh, it's fiber type distribution. But if there is. Another question, that follow up. Why are muscles not the limiting factor? Like, why are muscles have such a high extraction capacity that they're not what's limiting performance in economy?
Another question that I can't answer. Ask Martin, he would explain. Why do we have excess mitochondrial capacity?
Why do we have it functionally? Or
Yeah.
It controls substrate metabolism, so its use is more apparent in prolonged exercise. It's just that you don't need the volume of mitochondria you have to read the exercise. So your mitochondria can take more oxygen, and so it looks like it's a waste to have that many. But then when you go to do a 2-hour mode of exercise, they're beneficial. So it's just in the whole body max situation where they look wasteful.
Also, apparently it helps to maintain the intracellular PO2 low, which is going to help drive or keep the gradient high. So you're able to extract more. That's another explanation I've heard.
Yes, Tom.
For the blood flow restriction, I mean, I know you have the hemoglobin mass data and that didn't change. Do you have a guess when you see everyone else's data, what the difference, like what is the thing that is going to be responsible for the improvements?
I don't really, just analyzing all the leg blood flow and extraction values, all that takes time. And I don't have access. I haven't asked Kyle if that's been analyzed already. I'd be curious to see. It's going to probably take a while to analyze everything, like the biopsies, have all the data available. I know that almost everyone improved. So I think there's going to be an improvement of fitness. But of course, then there's the control group. We have to see what's the time of the year, it's spring, maybe everyone was outside training a bit more. So we don't know if the intervention was effective. I personally improved, so
You're not worried.
I think, yeah.
Did you maintain the improvement when you?
No, I lost it. That's another thing I didn't show here. In the first study where I was setting up the hemoglobin mass measurement, they also did a detraining phase. And they showed that if you don't do this for 2 weeks, you lose whatever benefit you gained. So yeah. It's not a pleasant way to train because it's super uncomfortable and you have this whole body distress. It's hard to describe. It's not just pain in the legs. You have a pain in the legs that you also have this sense that you're going to faint or something. So you have to have a supervisor, someone looking after you when you do it. It was set to the lowest occlusive pressure for each individual. So for most of us, around 200 millimeters mercury. It's not, so it's basically, it is full occlusion, but when you walk, you're gonna let some blood through anyway. It's at rest, it's full occlusion, but when you're getting the muscles moving, you're still gonna let some blood through. That's why you're able to do 20 minutes of it. Yeah.
What are the acute versus chronic effects of, like, say, EPO on blood volume? Like, does it adapt to maintain your hematocrit? Like, if it increases the hemoglobin mass, then do you, like, over time see that the blood volume increases?
Yeah, it would increase blood volume as well, but it's not going to catch up. If you take EPO, you're going to have a higher hematocrit and higher hemoglobin concentration than people who achieve it just by normal training. I'm not sure, like probably if you do really high, I don't know if it chronically would adjust so that your plasma volume would be kind of catching up with it. I can't tell for sure.
I guess similar kind of questions, like I'm thinking about how they say like train high, run low.
Mhm.
Is there like time scales based on how long that effect lasts? Like in terms of, or even just EPO use?
It's about 4 weeks, because that's the time course of basically red blood cell volume changes. Well, it's even in 2 weeks you start losing some if you come down from altitude to sea level. So you might want to time your competition in those 2 weeks. After that, yeah.
Still on a hematocrit percentages things. So this used to be the case a few years ago, and I'm pretty sure it's still this way. When you go to World Champs for Nordic skiing, first couple of days there, they take a hematocrit level. And at the time, I think 1 year I was there, it was 47%, and another year I was there, it was 48%. If you were above that, then you couldn't compete. But that level was the same for males and females. Is that fair? Should it be adjusted?
Was it the same for males and females? Yeah, I don't think it's fair. I think it should be higher for males.
Yeah, everyone I know who failed the test, which was not uncommon, and it wasn't necessarily a doping violation. Like it was separate to doping control. It was to be a safety thing, because at one stage they had people with artificially high hemocrits that would drop over and have all sorts of heart problems. Yeah, so I guess.
Yeah, I thought in cross-country skiing it used to be a hemoglobin limit, and it was different. I think it was 160 for females, 170 for males at some point.
Okay.
I didn't know they have like also a hematocrit limit that's the same for both sexes. That doesn't really make sense. Okay.
I've only heard of males who failed it.
Yeah. Yeah, 50 isn't that high. Like even at category level, hematocrits are a little bit higher than sea level, and like 50 is a normal value we see all the time. So.
I have one follow-up question to this. So if I want to dope, I want to improve my performance, I can take EPO, or I can perform blood doping. Intuitively, after this, it seems like it would be better to use blood doping than EPO. Is that true? Just because it increases total blood volume rather than just red blood cell count?
I'm not an expert. I'm not going to give you a recommendation on how to dope, but you better have taken both maybe, and testosterone on top of that.
I think like there's like a connotation where I just combine carbon monoxide with poisoning. But so like what's the time, you might have already mentioned this also, but what's the time scale of like things going back to normal after doing carbon monoxide?
Yeah, so the half-life of carbon monoxide in blood is about 4 to 5 hours at rest if you exercise. Just because the increased ventilation, you're going to get rid of it sooner. So it's not going to linger on for long. By the time you go to bed in the evening, it's going to be almost gone.
And then in terms of like that intervention, if you have people with like differences in lung capacity or say like COPD or something, like would they have different concentrations?
They might get rid of it a bit slower, because if you have high ventilation, you're going to remove the carbon monoxide faster. That's actually one thing we saw in the ramp tests. So the fit athletes, they reach higher levels of ventilation because they have higher VO2 max values. They would end up with lower carbon monoxide levels after the ramp because they were just really getting rid of it by the end of the ramp faster.
Should carbon monoxide be on the doping list? It is A, potentially dangerous, B, performance enhancing.
Probably, I don't know. I guess it has the same effect as EPO in one way. And it's dangerous. I guess it's also against the spirit of sport. That's one of the criteria for doping, maybe. So it could be dangerous as well if you don't know what you're doing. You just buy a bottle of carbon monoxide and start inhaling it. Like it could go wrong. Yeah.
I'm thinking people say who are hospitalized and they have difficulty like with recovery because of their reduction in VO2 max. Like it's a relatively like passive intervention.
Yeah.
So just to like kind of get them back going.
I haven't seen any studies using that. I think they'd rather give them EPO if they need to increase their red blood cell count. But I don't see why it wouldn't work.
any last questions for anyone? No? All right, let's thank our speaker again.